Hi, today I'm going to present HIDE, which is a system that uses passive data plane telemetry to detect and mitigate long-distance BGP hijacks. The core idea is to use changes in round-trip time to detect a very specific subset of BGP hijacks. This is joint work with folks from Princeton University and the University of Virginia. BGP hijacks continue to be a menace. That includes outages, for example, with Cloudflare in 2024, millions of dollars in lost cryptocurrency in 2022, and many, many others. To give you a refresher of how these hijacks work, let's take a client in Princeton and a US government website on the West Coast exchanging sensitive information. And let's assume there is an attacker somewhere in Europe who wants to snoop in on this information. And they advertise the same IP prefix as the US government website and uses some sort of method to make the new route seem more attractive, thereby drawing the sensitive information towards themselves. There is an even stealthier version of this attack where the attacker not only snoops in on the documents, but then sends it to the original intended recipient, thereby leaving the client and the server thinking that nothing is going on. Now, in HIDE, our central proposal is that we can detect such attacks using propagation delay. And so going back to this example, we observe here that the data under attack essentially travels many more thousands of kilometers, resulting in an increase in the minimum round trip time, which is really a proxy for propagation delay. And in our controlled experiments, we see that indeed there is a sharp change in the round trip time values when there is an attack versus when there isn't. The RTT has to be measured at a vantage point that sees both sides of the traffic, so either close to the client or close to the server. Now, where does HIDE sit in terms of the literature? BGP hijack defenses can roughly be divided into two categories, proactive and reactive. The proactive solutions are great, but there are challenges related to deployment in the real world. In terms of reactive solutions, the primary category is based on the control plane, and they rely heavily on BGP monitors that are placed around the world. Now, depending on the location of these monitors, these solutions can either miss certain stealthy hijacks or they can be slow to detect some hijacks, and therefore the attacker has time to cause harm. In terms of data plane solutions, they can be divided into active and passive. Active solutions essentially use probe traffic, but they rely on responsive endpoints and also cause probe traffic overhead. And hybrid solutions really combine control plane-based solutions with active probing-based solutions. And so they do not alleviate the limitations of either. Essentially, the part or the portion of this that is underexplored is passive data plane-based mitigation, and HIDE lies squarely in this space. But HIDE is not a silver bullet. It has several limitations. For example, in terms of scope, HIDE is really highly location dependent. So if the attacker is in the UK and the victims are in the US, it is relatively easy to detect that attack. But if the attacker is much closer, say in Canada, then it is much more difficult. Also, HIDE has a problem with accuracy. RTT under normal circumstances is noisy due to congestion, benign route changes, and so on and so forth. And so essentially, HIDE is not a general purpose defense, but it has several key advantages. HIDE can detect a very specific subset of stealthy hijacks, which is the part that is long distance that control plane often misses. It can massively increase the speed of detection because the change in RTT is visible at the client and the server immediately as the attack takes effect. Also, it can help with accuracy when used in conjunction with control plane-based methods as another signal that confirms attack detection. Also, by virtue of being in the data plane, HIDE can allow network operators to perform mitigation at a much finer granularity. So at the IP level, instead of at the IP prefix level, which is the minimum sort of possible subset for a control plane-based method. So we argue in this paper that HIDE is a very useful tool to have in a network operator's toolkit. So on the one hand, we have the limitations of HIDE, and on the other hand, we have its promises. And so this leads us to two main research questions. One is related to feasibility. How feasible is it really to detect long-distance hijacks using RTT? And in this work, we specifically focus on cross-country attacks, which often tend to be long distance because they're particularly harmful, for example, in cyber warfare or in case of surveillance, when the government of one nation state can launch an attack on another nation state. And so the second question is related to scalability. Let's say that RTT-based detection is feasible, but how do we then ensure that such a system can scale to the massive amounts of traffic running through a network? So more specifically, how can we perform hardware amenable change detection in RTT? So first, feasibility. We define feasibility in the following way. Let's say these are the min RTT samples in time for a particular flow. We divide the space into three parts. The green part essentially refers to what is observed under normal operation. So the top line essentially gives us the measured maximum min RTT before the attack, pre-attack. The yellow space refers to a buffer known as the surge threshold. This is a buffer we allow ourselves such that if there is normal variation beyond the measurement period, then we don't falsely flag this as an attack. But then the red zone is really where if the RTT goes, if the min RTT goes, we start to think that it's an attack. And the bottom of this red zone is determined by based on physics, essentially. So we compute the minimum distance that the traffic has to travel in order to go through the attacker. And then we use the speed of light in optical fiber, which is roughly 200 kilometers per millisecond, in order to determine what that minimum RTT could look like. So now coming to data sets, we essentially use the natural Earth data set, which has country border information for 258 countries. And for each pair of countries, say attacker country A and victim country V, we determine the best case attack scenario for the attacker. So we ask the question, what is the minimum perturbation in distance that the attacker can create and still launch a successful attack? So that's the best case attack. And we compute 258 multiplied by 257 best case attacks. And in order to reason about the measured attacks are defendable, and for the MLab data, 86% attacks are defendable. These are reasonably high numbers, showing the promise of HIDE. Also, the difference in the two data sets can be explained by the fact that the campus data has less noise in the RTT under normal operation. We also find that small and geographically isolated countries tend to be more defendable. For example, New Zealand tends to be one of the most defendable countries, whereas Russia tends to be one of the hardest to defend. We also ask the question, beyond country borders, how far does the attacker actually need to be physically for detection? And the answer is roughly as far as the hosts themselves or the victims themselves, but it depends on the noise in RTT as well. So to give you an example, if the victims are in New York and Las Vegas, then the attacker must be at least as far as Venezuela in order to be detected. But if they're closer, it's really hard to detect. Now, coming to the second research question, hardware amenable RTT change detection. The deployment setup looks like this. You have a client and a server, and the network operator is trying to defend against such attacks from near the campus or enterprise edge from a certain vantage point. And we assume that the operator has access to a programmable packet processor, for example, a programmable switch or a smart NIC and so on. And essentially, the stream of packets goes back and forth between the client and the server. So the switch does its normal forwarding as it would, but it extracts the packet headers as well and performs continuous RTT monitoring using a system called DART, which we built in 2022. And then DART generates a stream of RTT samples, which is then consumed by HIDE, which does the RTT change detection. And then if there is an attack, it installs rules in the forwarding plane to drop or rate limit traffic. So the second part of this is denoising the RTT. And the steps we take here is that we compute the min RTT in non-overlapping time windows. And we also aggregate the RTTs by /24 prefixes because the /24 prefix is the minimum subset of the IP prefix that an attacker can target with BGP hijacks. So just to give you an example, you have flow 1 and flow 2 with very noisy RTTs. And when we employ both of these methods to the right, you can see in the green triangles that the actual min RTT signal becomes very stable. Then finally, the operator has to provide certain inputs. And what they provide are target prefixes. So for example, the US government website and the threat regions that they fear there could be an attack from. And so what we do here is that we compute the best case attack from the combined area across those regions, those threat regions. And whatever is the physics-based min RTT that we compute, we call that the absolute threshold. So the min RTT, the measured min RTT, must never cross that threshold. Otherwise, we say we detect an attack. So in order to operationalize this, we have a profiling phase where we actually profile the RTTs under normal operation. And so that is where we calculate the top line of that green region, which is the measured maximum of all the min RTTs. One good thing about this is that it can be done entirely in hardware because it's just computing minimum and maximum over windows. Then finally, in the detection phase, we do change point detection. And the way it looks is that, let's say these are the RTT samples. They are, or the min RTT in time windows. And they are in the green zone, but suddenly they go from the green zone all the way to the red zone. And so we have two kinds of strategies here. We can say it's an attack. At the moment, the RTT is in the red zone, so that would be the blue star. We call that a two-window algorithm because you have one window in the green zone, the next one in the red zone. And then we can wait to see whether that trend holds. So the future min RTTs are also in the red zone. And in that case, we call it a three-window algorithm, and we wait until the red star to declare an attack. So to come to the evaluation, we compute optimal attacks from 257 non-US countries on each US-based prefix in our data set. And so we ask the following questions. What is the percentage of attacks that are defendable based on the absolute threshold only? And we see that 78% prefixes can be protected against 99% attacks, and then 99% of the prefixes can be protected against 75% of the attacks. Now, out of these that can be protected against, that are defendable given the absolute threshold, what percentage is defendable based on the search threshold? So we see that 99% of the prefixes can be protected against 91% attacks if we assume a search threshold, that buffer of 5 milliseconds. And if we want a higher buffer for confidence, for higher confidence, we can only protect against 64% of the attacks. Now, of the ones we actually try to detect, what is the false positive rate? So for 5 milliseconds, it's about 0.12%. And for 25 milliseconds, it's about 0%. And in terms of detection speed, finally, that really depends on the rate of RTT sample generation, which in turn depends on the data rate, but it generally is roughly between tens to hundreds of milliseconds. So in conclusion, we quantified the feasibility of RTT-based hijack detection. We designed HIDE, which is a system for scalable in-network detection of hijacks. And the future work would really be to combine HIDE with control plane-based methods to see how good of a signal it is in combination. Thank you so much.